Let's start off with the PowerPoint. So if you guys at home, you can always bring the PowerPoint up because I know it's not always the easiest to see on the video. Stokes theorem is actually just a generalized version of Green's theorem. All right, so for just a minute, let's take a step back in time and talk about Green's theorem for line integrals, not for flux integrals. Okay, so remember Green's theorem had two. There was a line for line integrals, for flux integrals. For line integrals, we summed up the curl, we summed up the circulation to get the line integral. Whereas for flux, we summed up the perpendicular to our path to get the flux. So this was Green's theorem. Green's theorem, basically what it did was it summed up all of the, all the curl, all the circulation. And we did it with a double integral over a region. But we talked a little bit about this last time, what happens with Green's theorem, because it's very similar to what happens with Stokes. If this is our region R. Yeah, there's a whole bunch of circulation going on inside. But when you add it up, it actually all cancels each other out. So all we really get left with is the circulation around the edge. And that's why Green's theorem works, where R is our region of integration. Stokes theorem generalizes that because Green's theorem is stuck in the 2D plane. All right, so our region had to be in the XY plane for Green's theorem. Yeah, we can only do a two-dimensional vector field. Stokes will allow us to work in 3 dimensions. So, for example, let's say we have the paraboloid 4 minus x squared minus y squared, which looks like this. And then C is going to be a path along the base. So you can see that black line there along the base. Well, what Stokes theorem says is if we have n, which is a unit normal vector with an outward orientation, in other words, pointing outward on the surface, and f is some vector field with continuous partial derivatives, then Stokes theorem says the line integral can be done as the double integral of the curl dotted with that normal vector over S. Okay. What that means, what the S is a surface as opposed to R, which is a region in the XY plane. So now what's happening is we're going over a surface S, but the same basic principle holds. All that circulation that's going on along the surface is all going to cancel each other out. So we only end up with the circulation that is along the base. And if that base is our path, is our C, then what we get is the line integral. Okay, so that's what Stokes theorem says. Stokes theorem is a surface integral. We talked about surface integrals last time. Remember, there were 2 different things. We did surface integrals of a function. We also did surface integrals of a vector field. We're doing surface integrals where the vector field is the curl. Okay. So mechanically, we're not doing something new. We have done surface integrals. Conceptually, it's a little bit new because we're using a surface integral in order to get a line integral. Okay. And we'll do this, we'll set up and do this example. We can do this as a function, or we can do it as a parameterization. We, of course, will do it as both because that's more interesting. So again, C does have to be the boundary, and just like with Green's theorem, where we have to be going counterclockwise, so the region's always on the left. Stokes theorem says the surface always has to be on the left. Not a big deal. If our paths go in the opposite way, we know we get the opposite sign, so we would just flip the negative or flip the positive, whatever we get. So, okay. We can do this via parametrization, just like we could do surface integrals via parametrization. So the curl would be our vector field dotted with our normal vector. Oh, sorry, you can't see the mouse I'm doing there. So just like last time, curl is the vector, would be like doing the vector field dotted with the normal vector. Same as last time. Our limits of integration would be the limits on the parameterization. Same thing we were doing on Tuesday, mechanically speaking. Conceptually, there's something new. Or we could do the curl, which is our vector field, dotted with the gradient. Again, mechanically, we did that on Tuesday. The only difference now is we're doing it to get a line interval. All right. So let's do it for our example. Like I said, we'll do it both ways. And so let's get a vector field in here to do this over. So vector field of 2y, 2z, 2x, and z equals 4 minus x squared minus y squared. We'll do this in both fashions. So let's start off. It's already set up as a function. Let's do it as a function. I'm going to cheat a little bit because the curl, remember to do a curl of a three-dimensional vector algebraically, we would do it as the determinant of a 3x3 matrix. So we can use a technology to find the curl, and we will. So let's go over to Maple and have it find the curl for us. Oh, sorry, wrong mouse. Okay. So Maple, I have to open a few packages for some of the stuff we're going to do. I'm going to put in our function. And I'm putting in the path. We'll talk about that later, but right now it's just so I can plot them together. And that's just that plot you were seeing before. So we have the surface and that black line is the path. Because we're actually going to do this one three ways. We're going to do the surface integral both two ways, and then we're going to go back and do this one via parametrization and make sure we get the same thing in all three methods, because this one's one we can do in all three. I put in my vector field. And so here's what's going on. There's our path is the red line. The green represents our vector field. I know it's kind of busy in there, but you can kind of see, get the idea. The surface isn't included in this one. And that we'll talk about as well. That's going to be a very cool thing too. There it is with the surface. Now, this is a command that's in Maple. The only reason I'm doing this is because we want to verify our answer. All right, -8 pi. That's what we should get for when we do this thing. So we already know what we should get. So what do we need? We need the curl, right? So let's go get the curl. So there's our curl. Again, I'm just using Maple. You could use, if you were doing this on the take-home problem, you can use Wolfram Alpha. Wolfram Alpha knows how to find the curl of a vector field. Just say curl of, and it'll find it. All right, so again, don't worry about the e to the x, e to the y, e to the z. It's Maple's way of doing ijk. So what do we know now? We know our curl of f is, what do we got? -2, -2, -2. Makes it nice and easy, right? Okay, now that's nothing new. We found the curl of a 3D vector field before, right? So again, mechanically, nothing new. The other thing we need is the gradient. So our function, and this is something that we had to do last time, what we'll do, we needed a function of 3 variables. We'll bring the z over to the other side, right? And we'll say, okay, well, our function g of x, y, z is going to equal 4 minus x squared minus y squared minus z. And so the gradient of g equals minus 2x minus 2y minus 1. Right? Again, gradient. We've done gradient before. Mechanically, nothing new. Now, the next step says we take the dot product of those two. You can see here, I've got the gradient, right, in Maple. Again, don't let the e to the ex, ey, and zz fool you. There's the -2x, -2y, -1. So the dot product will give us the integrand, right? Remember, dot product's not hard. And just a reminder, dot product is a scalar. So -2 times -2x plus -2 times -2y plus -2 times -1. So we're getting 4x plus 4y plus 2. There's our integrand. Last thing we have to do is integrate over our region of integration. Our region of integration, let's love it up here. Our region of integration is the shadow region in the XY plane. It's that circle of radius 2. Well, right now we are in rectangular. We probably wouldn't compute this in rectangular, right? We might switch over to cylindrical because of the round base. But right now, let's at least set it up. So minus square root of 4 minus x squared, the square root of 4 minus x squared, and then -2 to 2. In this case, I'm doing dy dx. And that's it. It's set up. Now, yes, as is, that's probably not going to be, this one's probably not going to be fun to compute by hand, especially. This is something that Wolfram Alpha or Symbolab could do, or we can convert it over to polar. It's really not going to be that bad, actually. So, what do we got? I went and converted it into polar, and I got 8 pi. Now, what did we say before the answer should be? -8 pi. Is that a big deal? No, because it's very easy to account for why we'd be off by a negative. Remember what we said last time, that there's 2 normal vectors for any given surface? We just chose the wrong normal vector. Not a big deal. Stokes theorem requires that the normal vector be pointing outwards. So let's go back to our normal vector. Our normal vector came from the gradient. So it was this guy here. Well, right off the bat, we can see we picked the one pointing downwards. We would want the one pointing upwards, right? If it's going to be outward off this surface. Is that a big deal? No, it just means we had the answer is going to have the opposite sign. That's the only thing it means. It's a real easy fix. So, oops. So all we got to do here, we change the gradient, and now there's our -8 pi. Okay. And so that is how we would do it in rectangular coordinates. Questions about that? Again, I know I sound like a broken record here. It's a surface integral. We were doing surface integrals on Tuesday, right? You guys have done some surface integrals either via the worksheet or in the homework. That's all. I want you to remember, that's all Stokes theorem is. It's a surface integral where the vector field happens to be the curl of your given vector field. That's all. That's the only difference. All right, let's do this one, same one, via parametrization. All right. So like we talked about last time, if we're going to do it via parametrization, the most important thing is to get the parametrization correct. So what do we want? We want an upside down parabola. We know it's going to be round. We've done a paraboloid opening upward. So now we want it to open downwards. So a parametrization that would work for this. So let's do it of u and v is square root of 4 minus v cosine of u. That's going to give it that downward shape. This is the only way to do it. This is just the way that I happen to do it. Square root of 4 minus v sine of u. And v, so that marker's a little later than I had hoped. Hopefully, you guys at home can see it. And as always, we need to give bounds on u and v, right? So clearly, v is stuck in between 0 and 4. We can't have a negative under a radical. And u is in between 0 and 2 pi. Now, Here's one of the nice things about parameterization. The bad thing is they can be a little tricky, right? It can take a little bit of time. But if I put this into Calcplot 3D and I get what I'm expecting, this upside down paraboloid, then I know I've got the correct parameterization. Okay, so we've got square root of 4 minus b cosine u, square root of 4 minus b sine of u, b. And b is going from 0 to 4. This isn't much better. And u is going from 0 to 2 pi. Okay. Now again, the nice thing about this is if our parameterization is correct, we should get exactly what we expect to see in Calcplot 3D. It should match that function exactly. So if we check, I get the exact same paraboloid. All right. Here's what's nice about that. If you remember, surface integrals, once we have the parameterization, everything else just follows, right? So that means we, our curl came out to be all constants, but if it didn't, we plug in our parameterization for any x, y's, and z's in here, right? And then that'll get dotted with the cross product of the partials. So all those steps stay the exact same from last time. So again, mechanically, nothing new. It's just what we're getting. The result is now something different. So first thing I do, I find the partials of, partials of my parameterization. Are they pretty? No. But could Wolfram Alpha or Symbolab handle those? Absolutely. Then we do the cross products. So that's our normal vector. Once again, Maple didn't simplify. This last one here would simplify down to just the -1/2. We do the curl. Now, again, because our curl is all constants, I didn't have to sub the parameterization in. But you remember we did that on Tuesday, right? If there were any x, y's, and z's, we put in our parameterization to get it. Oh, sorry, is that a little low? Is that better? And so the integrand comes now from the dot product of those two vectors. And again, our limits are the same as our limits on our parameterization. Once again, I got a positive 8 pi. Well, same issue, right? If I go back to my cross product, this component here, the z, came out to be negative again. But we know we need an outward facing normal. Z had to be positive. So we just multiply by a negative again. All right. Remember, the cross product is going to change signs depending on the order you do the cross product in. So it is something, to be aware of is, okay, we need to take that time and say, okay, is my normal vector pointing in the direction that I want it to? And just go off this, you can usually just go off the z component, right? Do you want the z to be going up or down? If we had a paraboloid opening upwards, we would want the z pointing down. Because it opened downwards, we wanted the z pointing up. Okay, so again, easily fixable because all we have to do is take the negative of our cross product, and then there's our negative 8 pi. Okay. So all right. Questions about Stokes theorem. So that's essentially how Stokes theorem works. And once again, just remember this, it's a surface integral. So the stuff we were doing on Tuesday, we were doing Stokes theorem. It's just a very specific case of a surface integral in that the vector field that we're using is the curl of the given vector field. Okay. That's it. Other than that, our surface can be anything. So just a couple notes on Stokes theorem and why it can be valuable. One nice thing about Stokes theorem is the surface can be any surface as long as its bottom path is traversed by, as long as the path is the base of that surface. In other words, we used a paraboloid that had, a bottom radius of 2. We could have used a hemisphere with a radius of 2. We would have gotten the same result. We could have used a taller paraboloid, but as long as that base was still the same size, it would have been the same. We could have used a cone, but as long as that base was still the same path, they all would have come out to be the same as far as the surface integral goes, because again, all the circulation on the surface will cancel each other out, and we just get left with what's around the base. So the reason that's advantageous is if we have a path and a 3D vector field, for instance, we can actually pick a surface that fits that path that might be easier to do. A good example is like a triangle. Well, we might be able to make the triangle to be a base of a plane, and then the surface integral gets really easy to do for that plane. Again, this does allow us to deal with 3D vector fields, something that Green's theorem does not. So it is an expansion of Green's theorem. Okay. Questions about Stokes theorem?